Hello, my name is Simon Tong, and this is my lab report for lab number 5 for Physics 2212. So a brief overview of this lab. The purpose of this lab was to use Faraday's law to observe how an aluminum foil tube would affect a falling bar magnet. The results found in this experiment would then be compared to a computational model that we made using GlowScript. A couple of key physics concepts we used were Faraday's law, Lenz's law, and magnetic flux. First off, Faraday's law is basically just how a magnetic field will interact with an electric circuit, comparing current with the derivative of magnetic flux. Lenz's law is that an induced electric current creates a magnetic field in the opposite direction to the change in magnetic flux. And magnetic flux is just how much of a magnetic field passes through a specific area. So the actual experimentation. After we recorded all the key values of the foil tube, we then found the north end of the magnet using the magnetometer app, which we used in lab number 3. Once we'd found the north end, we dropped the magnet north end first through the aluminum tube, recording the time it takes the magnet to drop. We then found the average of the five trials we did, and for mine the average was 0.31 seconds. Using a ferrous tube would not work, as the iron would interfere with the current and mess with the results, making those unreliable. So aluminum foil in this case worked much better than iron. Then my computational model. From this model, I got a time of 0.244 seconds. Comparing this to the experiment time, which was 0.31 seconds, these values are actually very close. As you can see, there is also a graph of velocity versus time, which is that sort of exponential curve as you would expect. So what we actually did to create the model. In creating this model, we first calculated the magnetic field of the bar magnet, given that its magnetic dipole moment was 3.2. We then calculated the current in the tube due to the change in magnetic flux, and using this we then calculated the magnetic force the tube exerted on the bar magnet as it was falling. Finally, once we had found all of this, we found the net force on the bar magnet, which allowed us to solve for the acceleration of the magnet, and from this we then back solved to find the time it took for the bar magnet to fall through the tube. So then into a couple of what-if questions. The first question being, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the following magnet change? If the resistance in the conductor was lowered, it would make it so that the current through the foil tube was greater, and the greater current in the foil would then cause the magnet to fall slower due to the greater magnetic force on the bar magnet from the tube. The second what-if question was, what if holes or slots were cut in the tube? How would this affect the ring currents in your model? Holes cut into the tube will not have any of the current flowing through these holes, making the magnetic force on the bar magnet smaller, and thus it will drop faster. Finally, in conclusion, first looking at a couple of possible sources of error. The timing for the experiment of dropping the magnet through the tube might have been quite off in certain points, as we were just hand timing when that magnet dropped to when it finished falling through the tube. And the actual time it took for the magnet to fall through the tube was not all that large, so that could have expounded how that error affected our results. Air resistance or other forces present on the magnet also could have played an impact in our experiment, as we weren't necessarily looking at those in the computational model, as we only really looked at the forces of the magnetic forces on the magnet as well as the gravity force. And then the magnet touching the inside of the tube also might have had an effect on how it fell, as it might have bumped into the tube ever so slightly as it was falling through. However, because the experiment and model results were so close together, I am quite confident that the correct results were achieved. If you would like to see more of the actual model's code, please click the link in the description. Thank you for taking the time to listen.